Good afternoon, everyone. Welcome to the second week of the course CS 470, Advanced Computer Architecture. I hope it was useful, the material of last week, to basically remind everybody of the basics, the basic ways we achieve performance in general purpose system in traditional processors. If you had problems to follow, I recommend again that you go and read maybe your bachelor course and bachelor notes on computer architecture, because it's going to be relatively important that you can follow well from now on. What we are going to do today is a major qualitative step ahead. We are going to look at truly what is dynamic scheduling in processors. That is the idea of executing in with much more parallelism programs. You have certainly noticed a blunder in last week recording. I'm sorry about that. You probably don't want to know what happened, but maybe I tell you anyway. I've been wearing this beautiful mic all the time long, just to discover much later that unfortunately the mic that was active is the one in the laptop. So that explains the poor quality of the audio. Hopefully now it is correct. Maybe at the end of last week it was already corrected. I can't remember. No, probably not. I want to blame, I wish I could blame Zoom for doing the mistake, but actually I really configured that myself 3-4 months ago, and it was for a good reason, except that I forgot that this was still active, this option was still active right now. So again, I hope this will be much easier to listen to. If you have problems, if you notice things, please, again, don't hesitate to send an email. So this is the situation as we left it at the end of last lecture. We started from a processor that was extremely simple, executing one instruction after the other. When one is completed, it starts to execute a new instruction. And this was a pretty realistic processor for the end of the 70s. What we had at the end of last week is that we have some overlap between the different instructions. They overlap in different phases of the execution. Remember something like fetch and decode, execute, write back, things like that. And we do have, like in this moment here, qualitatively, different instructions that, again, in different phases, are active, are executing in parallel at the same time. So we start having some level of parallelism, which means some level of advantage in performance. But we also have a number of issues that delay our execution, that prevent us from completely parallelizing all the instructions. Here is a list of the problems that we have encountered. Control hazards, the fact that every now and then between instructions we decide not to execute the next instruction, but maybe some other instruction somewhere else in the program. That is in the case of branches, and that this decision usually takes time to make, whether we continue with the next instruction or we go somewhere else to execute. We didn't look at this in detail last week, but I pointed you to either my slides or your textbook or your notes from your computer architecture course before. Typically, the point is that you need, in case you have a branch taken, you have to throw away some of the work that you have done in fetching and decoding new instructions that were wrong, should not have been fetched and decoded. we had the problem that we actually looked much more carefully of data hazards, so that is data dependencies, the fact that we produce values that future instructions are going to consume, and if these instructions that produce and the instruction that consume are too close to each other, they cannot be executed because the result is not yet there. And the way that we have solved the problem is that we had to stop, essentially to nullify the advantage of the pipeline by stopping the instructions that depend on ongoing on results that are being computed until this computation is finished, and then they can advance. We try to improve things with bypasses and so on, which work in some cases but don't work in every case, and may not work so well in pipelines that are a bit more complicated than the simple one that we looked at. And then there was another problem that I think I mentioned at some point, but was not necessarily very visible in the example that I've shown, which is the fact that we have to constrain every instruction that can be executed by a processor, so the complete instruction set, should be constrained in the same pipeline, should follow the same sequence of execution steps. Now, we don't see it so well when someone teaches us how a pipeline works and usually picks an architecture like MIPS or NIOS or RISC-V these days, because they are architectures that are designed to have an instruction set that is extremely regular and therefore relatively easy to achieve what I just described, that is, have the same phases for every possible instruction. The fact is that instruction set that came way before MIPS, like the x86 Intel instruction set, don't look at all like this, so they look extremely difficult to bring into this world of very rigid sequencing of the different phases of execution. For instance, there are instructions in the x86 instruction set that need more than one memory access on top of some calculation, right? And so if you look at the pipeline that we had last week, right, we had an ALU phase plus a memory phase, or two cycles of memory phase. It means that we can maybe compute an address and then do an access in memory, but that's all we can do. And in fact, this is exactly what is in the MIPS instruction set. But the moment I have an instruction that computes an address, goes and fetch something from memory, computes some other address, gets and fetch something from memory, makes some operation and saves this into a register, well, maybe the example is not perfect, but similar to what you can find in x86, you can see that this doesn't fit at all a simple pipeline like the one we have. And we need to have phases for basically every combination, and it's going to be a mess. On top of that, architectures that came later than MIPS, and MIPS itself as it evolved, may have new complexity in forms like floating point instructions that don't take only one cycle to execute, but maybe multiple cycles, in some cases maybe several cycles to execute. And of course, these contrast with instructions like integer, that take exactly maybe one cycle is perfectly enough. So this rigid sequencing didn't look to be too much of a problem in the simple example that we looked at, but in the global picture, the fact of coercing every possible instruction in the same framework, of having this simple RISC instruction set, is a big constraint that may be difficult to handle in the most general case. So before, let's move on to what we can do, and actually we'll come back to these different problems, and we'll see that some of these will go away by doing something quite dramatically different. Before you continue, let me remind you of some decision that we took last week. At some point, we had this problem of the dependencies, right, that we just evoked. And we had sort of we thought of two ways to go about it. One, which is what indeed in the end we implemented, was to try to fix our pipeline to do something so that the execution of our programs would remain correct despite this problem, right? You remember we added this logic, these comparators that would detect that there is a dependency, and given the dependency would stall, which is a different way to say that essentially we introduced at runtime during the execution no operations NOPs in between the operations written in the program. So this was one of the directions that we could have gone. The other direction that I evoked last week was to say, okay, that's what the pipeline does. The pipeline does not honor these delays, the fact that there is a latency before we can actually use a specific value. So the next instruction will not see the new value. It's a fact of life. Let's accept it. Let's not modify anything in our hardware, and let's modify the program instead. And what that implies is that, for instance, we need to, if we really have a dependency and we need to honor this dependency, we'll need to introduce an appropriate number of NOPs in between so that somehow the consumer of the instruction arrives to the decode stage sufficiently late compared to the producer so that the value is in the register file. And this was a completely different approach because, again, one is a sort of hardware solution for the problem. We needed to add logic to our processor to detect the problem and act. And in the other side, it's only a software problem because we don't modify anything in the hardware, but we go back to the compiler or to the programmer and we say, please write your program differently. We are changing the semantic of the instruction and of the code. So it's your problem. Change something and in the end achieve more or less the same result. One thing that I did not maybe mention last week related to this, and maybe it's at least sort of fun to know and maybe useful in the first homework when we will be talking of the R10000 to note from this point already, is that MIPS historically made a fairly strange decision, you may say. This problem of dependencies exists both for the data dependencies, data hazards, and for the control hazards, right? You can do exactly the same for the control hazards and say, the next instructions after a branch, I will execute anyway because they enter the pipeline, and I will not try to detect if I need to cancel the coming instructions. They just happen. Right? We'll make this a little bit more clear in a few lectures when we will talk of prediction. But point is, MIPS has decided to introduce dynamic stalls in the case of data dependencies and asked you to modify your code or to know that there are so-called delay slots, that is, two instructions after each branch that are executed anyway. It's very counterintuitive, right? I write a branch and the two instructions after the branch will be executed anyway, as if they were before the branch. And if your software is not written like this, you have to do it. If you don't want to modify too much your software, the minimum software modification that you have to do, there is a minimum that you have to do in software, is to add a couple of NOPs after every branch, and that will make at least correct your code. So these two directions are very different, and we are spending quite a bit of time today and in the coming few weeks in looking into this part, which is called the dynamic scheduling solution. And you understand the word, right? The dynamic in the sense that it is during execution, scheduling because we decide when to execute things and when to withhold things from execution. And the other possibility is here, which is the static approach. Static in the sense that we do this before anything starts to execute, and we solve any problem that we have at the time of compilation, of generation of the code. And about this we will spend a few weeks, but much later. And it will be a very important difference, the difference between these two approaches, and the implications will be a theme that we will come back over and over in this course. I want to also take this time to re-emphasize something that I'm sure I said last week, but is important in this duality. Where hardware is the main actor, is the one that takes care of things, if I change my processor, I change the hardware, the new hardware will take care of things in an appropriate way. In other words, my code will never change for this class of processors, right? I will keep changing my processors and my code will be always the same. I will achieve what people call binary compatibility. And the situation is exactly the opposite in this realm, right? For instance, think of last week, if I remember correctly, and the number is not particularly important, but if I remember correctly, between two operations in the ALU, if I have an operation in the ALU that produces a result and the next instruction uses this, it's too early, and I need to introduce exactly 3 NOPs to get things to work. But these 3 depends on the pipeline that we have shown. If I had the memory not taking 2 cycles, remember there was an M1 and an M2, but there was an M1, M2, and an M3, so 1 cycle more, before I can reuse the result of this ALU operation, I need 4 cycles, 4 NOPs before putting the consumer of this value. So my code changes as I change the processor. The more I change, improve, modify my processor, when I change my processor, my code is not going to work anymore if I don't recompile. Achieving binary compatibility is extremely important from a commercial standpoint, right? You have your PC, you have a bunch of software that you have been purchasing, and at some point, or developing even more, and at some point you decide to change and upgrade your hardware to a new processor, and you want everything to continue to work. You don't want to go to Adobe and say, please recompile everything because I have a different version of the processor. You don't want to have, if you are Adobe, you don't want to maintain 76 different versions of your binary depending on exactly which model and which version of Intel processors you have. So Intel has always been moving in this direction, and this is the direction that we are exploring at this point in time, where we maintain binary compatibility by creating and by changing the hardware in such a way that we do a better processor, but at the same time we honor the original code that was for the previous generation. But now I wanted to remind you of this, to go back a little bit to, again, something that we have seen last week, one of the things that we said is when we are using the static approach and we are introducing knobs in between the instructions because we need to separate them enough to have a correct result. One of the things that we said is we could look around and figure out if there are instructions that are independent from these two, that don't need to wait for this value, and therefore we can execute them in place of these knobs. And this would even improve our performance. One thing that I want to notice is that this reordering of instructions is also possible in the dynamic approach, right? I could still have a compiler that tries as much as possible to reorder instructions so as to make sure that there are no or there are less knobs dynamically generated because there is already something in between that is being done. What we are going to do today is actually to try to do this reordering dynamically. Not the compiler does it and we obey correctly to this, but we try to generate the new order in a dynamic way during execution in hardware. So here is the idea. That is exactly what I already described, I just described. Suppose that you have this program written like this. I have a divd and add immediately after that consumes the value that the previous divd generated, and assume that divd is a longish operation, is a floating point division, and therefore I need to wait a number of cycles for the F0 to be ready. Suppose that I have a third instruction that has nothing to do with the previous two. It uses two values, F8 and F14, that have nothing to do with the results that the previous two instructions produce. The idea is that as soon as I'm starting to execute divd and the result is not going to be there for some time, I don't want to execute add d because I can't, but I want to start and go execute divd. So what I want to do is to execute this program out of program order, out of the original order specified, of course maintaining semantic correctness because otherwise it doesn't make any sense. And I want to modify my machine to be able to support this new paradigm, new idea. What do we need to do this? How are we going to achieve this? So let's look at this image. We can still recognize somehow the pipeline, right? We can still recognize here our fetch, decode, and so on that ends up into the write back. But we need to change things a bit, right? The first thing that we need to change is that before we had here in this level a single register, right? The same register as this one qualitatively, right? And we will fetch, decode, and put there the next instruction. And this next instruction would stay there or be replaced by an op and so on if there is a problem with the dependencies. Now, if we want to go and look for further instructions that can be executed, we cannot block the fetch and decode stage, right? We need to continue fetch and decode new instructions until we find one that finally we can execute because it doesn't depend. So what we need to do is we need to park somewhere, put somewhere the instruction that cannot be executed. It cannot go on ahead here, but I need to be able to bring here new instructions. So I need to park it somewhere. So I need to fatten up, make bigger this register, this pipeline register must grow in size and allow me to put there instructions that cannot advance, but should not block me from advancing the fetch and decode. Okay, so somehow this register has become multiple registers of the same sort. The second difference that we are doing here is that instead of having a single pipeline here, we are putting in parallel the different types of pipeline that correspond to different type of operations. For instance, we have here the ALU, we have here the memory access pipeline. Notice, if you remember a bit how the pipeline was last week, that we had the memory access that was an ALU, a memory instruction will go through an ALU first and then spend 2 cycles for the actual memory access, maybe one for sending the address to the memory and the other one to get back the result from the memory or cache or whatever it is. So 3 cycles for memory because the ALU will be potentially needed in, we are talking of a classic MIPS-like instruction set. We need the ALU before the memory access because we have to compute some address. And notice that here I'm consistent with this idea because I have the memory that takes 3 cycles. This is what this 3 means. And what I imagine is in here is a pipeline itself that I'm not showing explicitly, but is a smaller pipeline where I have an ALU and the same M1 and M2 cycles that I had in the previous operation. So now I am decoupling the different types of operation. So I have this advantage here. I'm breaking this problem of rigidification of the pipeline, of constraining every instruction in the same framework, because actually now I'm not at all constraining to the same framework. The ALU instructions will go through here, and the memory instructions will go through here. And now if this is much longer and this is much shorter, it's okay. Actually, it's great. If I have something that is ALU, it will emerge from this pipeline faster and maybe sent to the register file faster. And we'll see that maybe we don't want to do that. What happens here? One thing that happens that certainly was not happening before and now can happen is that we may have 2 writes at the same time that try to go in the write back. So here there was again one register like this, a pipeline, a simple pipeline register. Now we need, at least for this reason, a little bit more space in this register that becomes also a little bit more fat, so that we can store, for instance, one result while the other results goes out. We'll see that actually we need much more in this place. Okay, so this is a bit the sense of what we have, and I think we have the sense that at least we can do this reordering because now I can fetch and decode continuously, bring new instructions here, and try to feed the execution units with instructions that don't have dependencies. I can discover the absence of dependencies. So we have essentially 3 problems to solve. One, which we just mentioned, are these structural hazards. What does it mean, structural hazards? Before we had only control hazards and data hazards. So the fact that there is a control dependency that we don't know how to handle. We have a data dependencies that we don't know how to handle. Now we have a new problem, which is, for instance, that there are 2 values, one coming here and one coming here, that both want to use the write back. So we need to find a way to handle properly these things because they just didn't exist before. Before we had this extremely rigid pipeline and everything was ready by construction. We have the data hazards like the ones before, the read after write, the fact that we go and read a register where a previous instruction most recently tried to write a value. So this is exactly what we are sort of comfortable with because we know exactly this problem. And then we have these two other data hazards that we have ignored last week, but we'll see that we'll see in a minute why we ignore them and why actually we cannot ignore them anymore. So how are we going to handle these data hazards? We say that before the execution units, what we need is not just one register for the instruction that has just been decoded and that will or will not continue execution, but we need to park there instructions that we cannot, in fact, execute now, and continue to do so, continue to decode new instructions until we find something that we can execute. So this buffer looks like multiple rows similar to the single register that we had in our pipeline. And here it is. It's called the reservation station, and it contains a few things that we are familiar to. The moment the fetch and decode unit comes up with a new instruction, it will decode that one instruction is, for instance, an add, and that the two operands are register 1 and register 2 or whatever they are, and it will go and read the values from the register file and bring from the register file here the values. Now, of course, we have the problem of dependencies. Maybe what is in the register file is not the correct value. And again, this thing will not continue. This instruction then will be sort of killed and refetched and redecoded in the previous pipeline. Here we want to just drop it here and continue to look for the next. So what we want to do is to put here all the operands that I can read from the register file and leave a hole, leave an empty space for those that I cannot read. So suppose that this was an add R1, R2, R1, I know that there is no dependency. I read it and I write here the value. R2 is not ready yet because it may be produced by just the previous instruction. So I leave it empty, so to speak, invalid. Of course, I need to leave some information about which instruction of those that are ongoing in the pipeline will produce the value that I'm interested. Which value is this one? So I have two things, two columns in this data structure that are new compared to what we had before, right? Before, in this intermediate register between the decode and the execution phase, we would have only the operand and the arguments, or the operation code and the operands or arguments of this operation. Now we have also these tags, these labels that are mutually exclusive to the content of the two columns about the operands. In other words, if I find an operand, I don't need any label, the operand is there, we are happy. If I don't have the operand, I need to have a tag to recognize the value that I want. And the idea here is that when I will have both of them, I will start executing and take from the reservation station the instruction, do the operation, propagate it with the tag of this instruction so that it will come back. This is sort of connected here so that all the execution unit, all the functional units produce and show to all the reservation stations all the values that are being generated in a specific cycle. And I will tell this instruction that I call ALU3 has produced the value 1000. Is there anyone in here that is interested in this value 1000? We'll go in here, look at whether there is the tag ALU3, there is here the tag ALU3. So it means that this instruction waited for this value. I suppress the tag because I finally found the value, and this value is 1000 that I can put here. So next cycle, I can look at this second entry in the reservation station. I have 1000 here, I have this horrible value here, so I have both values. I can configure and start the ALU to do this operation. Okay, so I hope you get the sense of how this works, right? I put here all the operands I have. When I have all the operands, I start the execution through the execution unit. When any execution unit, including myself, including my own execution unit, but also of the other execution units that are around me, I have completed something, they announce it through the tag. They say the result of this operation is such, and I keep completing my table. By completing my table, I have more instructions that can be executed. I can execute, and so on and so forth. You see that we achieve what we set to achieve, right? We have out of order execution, and we honor read after write. We honor read after write because we don't let an instruction for which something is missing start. As soon as some instruction is ready, whatever is the order of that instruction compared to the others, if it has the operands, we let it go. It's clear, I hope, that this data structure then is not an ordered data structure. It has no first and last. It's not a list that starts somewhere and finishes somewhere. It's just what I call a parking lot, right? Like in a parking lot, if you cannot advance and you have to leave your car somewhere because the road is closed, well, you look for one of the parking lot, you find one empty, because if it is full, you cannot put your car. Where it is empty, you go. It doesn't matter if it is the first, the second, the third, right? It must be there. And here is the same thing, right? You have seen, for instance, that we understand by the fact that the tag that has been used here to identify the source instruction is this one, is the third, that this instruction must be in the code after this one. So you see that they are reversed inside the reservation station. But again, this is completely per chance. It's completely irrelevant where they are. The next one that arrives, I'll put it here simply because it's the only place that I have currently in the reservation station for one more instruction that I need to decode. Good. Now, there is one question. If we have a sense of how this mechanism is going, one question that I have for you is, why did I use this tag? I use this tag, you have seen, I use as a name of which instruction will generate this value that I'm interested in. I use the name of the reservation station where the source instruction, the producer of this value, is currently parked. So I hope it is okay for you, right? I don't see why this will be necessarily a bad choice. What I will comment is that maybe it's not a natural choice, right? Maybe I could have decided to use something more, maybe less, more straightforward, more direct. And so I want to make a pause, and I want you to invite to think of what could have been a different tag. If there is a different tag that I could have used to identify the source instruction, and why maybe that would not have been a great idea. So there are at least a couple of ideas of other tags that seem to be fairly reasonable. But both of them have for similar reasons, but in different ways exactly. the same problem that makes them unusable. And I think it's good that we look at what is not usable as a tag. So I'll make a little pause and I let you think of at least one example. So what other tags or names could have I used instead of what I chose in this slide where I have used the names of the reservation station? What would have been more natural? Not that I put here, I wrote here at the bottom right of the slide a possible code that corresponds to the occupation of the reservation station in this moment, so that we can use an example for understanding. What are the other possible tags or the other possible names for these values that we are using, that we are waiting for? I think the first and most natural answer that I would expect from you is the register name, right? This operation here, this mul_d, produces a value that will be put in F2. So in some sense, you can look at F2 as the name of the result. So one could have said, why don't I put, instead of mul3, here in the depending instruction, this instruction is this add_d that we find here, and the second operand is F2, why instead of using a name mul3, as I've done in my example on the slide, why didn't I write here directly F2 in tag 2, and I wait when F2, the value of F2 is computed? Superficially, this seems to be a perfect thing, right? When I decode the instruction at PC at address 124, the add_d that when I decode the next instruction, the one at address 125, the sub_d, and I find that there is a dependency between this F5 and this F5, why do I have to put ALU3 as a name of what I'm waiting for? Why don't I write simply F5? So I promise that this looked like a good idea, or actually looked at least as a natural idea, but has a problem. What is the problem that we have with this idea of using the name of the registers as tags? Well, I think it becomes clear if we continue and decode one instruction more, the one at address 126, which is an add_d. We need to find one place where to put is a new instruction that is not among those that are already in the machine. So we have to put it in the machine. We put it here in the reservation station, is the only free place, and is an add_d, and it has two operands. One is F2 with a dependency here and here. So from the sub_d, but I write, as we promised to do, F2, and it has F7, which is ready and has no dependence. So F7 is a number that I get from the register file, so 1, 2, 3, 4, or whatever it is, right? So there is no argument 1, there is no tag 2. I suppose that as soon as you look at this now, it's absolutely clear why the name of the register, why the register is a bad tag, right? What is happening here that is absolutely horrible is that now I have here F2, this first line of the reservation station, or first reservation station, is waiting for F2. This one is waiting for F2. So now when there is a value that arrives here and says, oh, someone has computed F2 and the value is such and such, I will believe that this is the value that is both going here and going here. And this is wrong. And this is wrong because essentially the register names are not unique. I call, because I have a limited number of registers, so I have to reuse them in my code, and it's totally legitimate to do that, but I call different values with the same name, because I put them in the same register. So the key here is that we need to have as a tag something that is non-ambiguous, something that is absolutely unique. In some sense can be absolutely anything we want, but it needs to be unique inside our processor. So what is another idea that we might have? That is another idea that some of you might have thought of in the previous break, which is, for instance, to use the program counters, right? Again, I need something unique, something that identifies the mul D from the add D from the sub D. And at least superficially, it may seem that these are, in some sense, more unique, right? So I could say, oh, no, instead of putting these values as tags, what I could put is the PC of where I found the instruction, so that here I put 1, 2, 3. I chose a bad color because we don't see anything, so let me choose another one. This is 1, 2, 3. Then I have a dependency here, and I need the 1 to 4, the result of the instruction at address 1 to 4, and here is the result at address 1 to 5. Sorry, it's here, 1 to 5, right? So this seems to superficially, again, work better, right? For instance, now we don't have absolutely any ambiguity between these two instructions. Now, if we think a little longer, this has essentially the same problem. Can you think why the problem is not gone away? It's just in a different form. Well, the different form is that I may have a branch here, and I may be repeating this in a loop. So at the same time in my machine, there could be two versions of instruction 124. And so again, I have an ambiguity because now I would have, in a larger, of course, reservation station, I would have potentially, there is at least this possibility, that there are two copies of the instruction at PC 124. And now again, I'm aliasing, I'm ambiguous between which one of the two loops, of the two repetition of instruction 124 we have. So I hope this makes a bit clear this problem of the tags. The problem of the tag is that we just need to select something, and it really doesn't matter what it is that we select, but something that is unique inside our machine. And the selection that I've done, the solution that I have in this slide, which is far from being the only one or the best one, is to use as a tag the position of the instruction inside the reservation station. Why is this a good idea? Is because there can be only one instruction at a time in the machine that is occupying ALU3, and therefore it's non-ambiguous. We have to be careful, and I will not be careful, but I tell it now, we have to be careful if we are designing this machine exactly in this form as I'm describing. We have to be careful when we let let's say we deallocate this last entry in the reservation station. One could be tempted, and actually maybe I will say sometimes this, but is incorrect, that as soon as I launch the instruction, actually we will use the word issue the instruction, I'm ready to execute this instruction because maybe I got finally this value. The moment I start the instruction, I will be tempted to suppress this this entry in the reservation station, and I hope it is clear why I will be tempted to do it, right? I know what are the arguments, I'm passing them to the ALU. I know what is the operation, I pass it to the ALU2, and I know the name of this, and I pass it to the pipeline, sort of in some sense to the ALU or to the functional unit to propagate further after the execution unit and to announce the result to everybody. So I don't need this anymore, right? So I could be tempted to take this one that indicates validity or occupancy of this reservation station and immediately say 0. I don't need this anymore. And although it is correct in some respect, it will create a problem in terms of unicity, right? Because now I have this ALU3 operation that is somewhere in the ALU and will take potentially several cycles to go out. Doesn't matter if this is an ALU and maybe it takes only one cycle. Imagine that it is a floating point unit and it takes 10 cycles to come out from this from this path. And now I have a problem, right? Because if I have suppressed this entry, the fetch and decode unit may come with a new instruction and put it here. And now I have another meaning of a ALU3 that is different from the ALU3 that is somewhere here on the pipeline. So you understand that, and again, this is something that maybe I will not say correctly in some cases, it's just a detail, but an important detail that has to be taken into account when I cannot deallocate the entry from the reservation station until its corresponding result has been announced. When the corresponding result comes out of the pipeline and has been announced to anybody, and everybody has replaced its own tag ALU3 with the value that is announced, this is the moment that I can have a new ALU3, because basically ALU3 has disappeared from all the tags, and so ALU3 is a tag that can be reused. So there has to be a little bit of attention in how I use and allocate and deallocate the entries of the reservation station. But again, maybe you can see this as a detail. Still an important detail, because if you get it wrong, it will not work. We have taken care of the first and maybe in some sense primary problem, this one of the data hazards. The reservation stations are our instrument to do that. We park their instructions that are not ready. We have absolutely unique identifiers to know what we are waiting for. We tell to reservation station every result that is happening, that is coming out from the functional units, so that they go and fetch what they need to try to have new instructions ready. When they are ready, they advance. So problem solved. Now we have to take care potentially, and I'll show you why we have to take care of the fact that there are other types of hazards, like the write after read and write after write. So I think probably everybody is familiar with these names, but maybe it's good to see a couple of examples here, right? So what we have been discussing so far is this kind of dependency, and is what people call a true dependency. Is a true dependency in the sense that I'm really actually waiting for something. I depend on these instructions to finish. If it doesn't finish, there is absolutely no way whatsoever that will allow me to start this instruction, because I simply don't have the operand. So again, we call it a true dependency. There are two other types of dependencies that are equally dependencies in the sense that equally prevent me from reordering instructions, which are dependencies like this. I do write a value in F4 just after reading a value in F4. So let's first convince ourselves that this is a dependency, is a constraint on my reordering. If you think of moving this subd instruction in between the divd and the add, advancing it, which is the game that we want to play now, of course, I make a mistake, right? Because I put a new value in F4, and after that, I read the new value instead of the old value, which was what was written here. So it is a dependency. The same is true for this write after write. I write twice in F0, I write this value and I use it, and then I write a new value, and then probably I will be using it. So again, it is a dependency, right? If I do this add before the div, of course, is a mistake, because the user of this F0, which is somewhere in the code that is not here, will see this value, the sort of first value for F0, and not the second value, because the second value has been written first, so has been overwritten by the time that we get here. So once more, both of them are constraints that I have when I reorder. Yet they are a bit special compared to the dependencies that we have seen before, to the read after write, and people call them false dependencies or name dependencies. And the second, calling them name dependencies, is maybe particularly illuminating, in the sense that the dependency is not created by the data that go through register F0, like in the case of the red arrow. In the case of the green arrow, the problem is exclusively the fact that we are using the same name for the register. This is made clear in this slide. If I change the name of the second F4 of this F4 in the third and the fourth instruction with any other registers, I call it F4B here, but maybe you say, oh, F4B doesn't exist, it's not a register, call it F7, call it F31, it doesn't matter. But if the moment I use a different name, the dependency doesn't exist anymore. And this is the sense of the false dependency, right? It's a dependency that I can remove if I use differently my registers. It's a dependency that exists because I have a limited number of registers, so I cannot always get rid of this dependency forever, I mean, in every possible case. But if I have some additional registers that I can use, I can remove it. And of course, the same is true for F0 and F0B, again, in the example, and you can still think of F0B as F9 or something else. The point is, again, that the dependency doesn't exist anymore just by changing the name. So it's a very different type of dependency, and is a dependency that we can, in some sense, work on to make it, in some sense, disappear. So before continuing and trying to look at this renaming, maybe the first thing to do is to convince ourselves that we have a problem, and maybe, first of all, even that we didn't have a problem. So let's look at this program with these two fake dependencies between F4 and F0 in our old pipeline, in the pipeline that we did last week, right? In that pipeline, we have prevented the execution of a dependent instruction, a true dependence. We have prevented and delayed it until the operands are free. And everything happens in order. The moment I stop the execution of this one, I stop the decode of this one, and the cycle later, I stop the fetch of the third one. So everything has been shifted to the right. I hope it is absolutely clear. It's what we have done last week, right? It's the stall and the introduction of these virtual knobs, if you want. But then it is absolutely clear that neither the write after read nor the write after write will ever be a problem for us. It's very clear, I guess, to everybody that any write back of an instruction following some other instruction will always happen after the read that is the decode, that is the read of the register of a preceding instruction, right? So the write after read will always happen. Whatever happens in terms of pipeline scheduling will always be after the read, so will never be violated. The same thing applies here in the write back. Since I stole everything and since all the instructions arrive in order to the write back, again, in every case of a write after write dependency, the second write is always after the first write, so the dependency is honored. Things are a bit different now, right? Because now we are accepting to execute, here we see the third instruction, even before we execute the second, because the second has this real dependency, so there is absolutely nothing that I can do except waiting for the result to be ready. And I hope you are starting to get the feel of what happens in our machine. Right here, there is the result of this instruction that is propagated from the execution unit to the reservation station. So at the end of this cycle, it is recognized by the second, by the reservation station where the second instruction is that the operand has arrived, and therefore the next cycle can be read. But this the third instruction, once is decoded, enters the reservation station with two values that, since they have absolutely no dependency, F0 and F3, have nothing to do with the operands that I need, so I can go and read directly from the register file. Since I have immediately every value, I start to execute, right? I start to execute and potentially I go into the write back. So it is still true that the write back of a later instruction is always after the decode of a previous instruction. So on this side, maybe we don't have a problem, but we do have a problem with the order of the write backs. Unless we do something, we will have the write back that don't happen in the correct order. So for instance here, because this instruction is independent and can be executed, the write back will be naturally here. And if we do here the write back, writing the two values that I write in register F0 get written in the wrong order. So if I want to be correct, I need to delay this write back until the first write back is done, and I suppose that in this cycle there is some other write back that is being done, so I cannot do two at the same time because there is only one port to the register file, and finally I do. And this is the only way that I can be correct, or this is, I mean, compared to this one, but I need to do it. Now, I think you are convinced, I hope you are convinced that I need to do something about these write after write dependencies. But we said, if I come back to what we said before, that all these dependencies simply go away if I change the names, rename the destination, rename the values that I'm waiting for. And this is what we have done before. So in reality, because of all the discussion that we had before about unique tags, this problem is somehow solved. At least it is solved inside the processor for propagating the values between the different units. Let me go back to this example, for instance. I am not calling, if you remember our discussion before, I'm not calling this F0 like the programmer called it, but I'm calling it with a new name that I invent at the moment I'm executing this instruction, and this name is unique. Is the name, for instance, in my example, is the name of the reservation station where I am going, where I have put this instruction at I. So I'm using a unique name, which is completely different by construction from this one. Since it is different, is exactly what I see here on the right on this in this diagram here. There is no write after write. When there will be a new instruction here that consumes this value, there will be no ambiguity about F0 or F0B, because this will be called with one specific name of the reservation station that is not this one. So what I'm doing is that I'm doing an implicit register renaming. I'm just by choosing something else as a tag, what I'm doing a register renaming, but the name that I'm using is not really a register name, but is another name which has this unicity. Now, we still have a problem when eventually we will need to put the value in F0, because our programmer in the end knows that here in F0 there should be a specific value. So I cannot rename too much. I can rename for my own sake, but I cannot rename too much for the user. And this is exactly the next problem that we need to face. And we are going to express it in a slightly different way. The problem are exception. How do we handle exceptions in this case? There is a little joke that I always say to the students at this point, and maybe is especially valid when the exam is an oral exam. I always say, if we are doing the exam and I'm asking you what is the problem of something, whatever it is, and you have no idea what to answer, well, if you want to have a guess that has a probabilistic chance to be correct, say exceptions. Exceptions are always what creates problems in our machine. So it would be much easier to live, and in fact, it has been easier for people to design processors in the 50s, 60s, because there were no exceptions, basically. And so everything was much easier. I'll come back to this point a little later, maybe. But why exceptions are a problem? Exceptions are a problem because they are a moment, or they are a mean for the for an external observer, for a programmer, if you want, to see the state of the machine. Maybe I go back a couple of slides, right? I said here, the programmer knows that here in F0, there must be a specific value computed by the add I, right? Because that's what the programmer has specified here. So when we are past this instruction, this is what the user expects. Except that the user cannot be there to see it. You see what I mean, right? I mean, I'm doing the right thing inside because I'm using a different name, so everything is fine. Who can tell that I don't have the correct value in F0? And this is exactly the problem of exception, because exceptions show the state of the machine. Because what happens in an exception, right? In an exception, I am going to suspend the execution of the problem, right? Remember that one type of exception, the name can, everybody has different names for these things, but I call exceptions all forms of interruption of the execution, and interrupts those that come from IOs. An interruption is, in a sense, is a nicer name, because this is what it is, right? You interrupt the execution of the program. Maybe actually I want to do now a little parenthesis, because maybe it's part of the reminder. I hope everybody is clear what exceptions are in a processor. Exception is a highly in programming, you would say probably overloaded term, right? There are many different meanings of the term exception at different levels. You have Java exceptions, you have exceptions in the maybe operating system. Exceptions in hardware mean that there is one instruction, or there is some phenomena that makes the sequential execution or the programmer specified execution be interrupted, and with some semantic precise definition or some standardized way, go and execute a different piece of code. Okay, so it's one situation where the programmer of a single program of the whatever I'm writing application, I am not in charge of the control flow of what is the next instruction that is being executed. I hope we are clear, right? Normally I am, right? Because I do a branch or I don't do a branch. I write a branch and then maybe I'll go to a destination. I wrote it, so I'm in control. Or I don't write a branch, I write a normal instruction, so I know that the next instruction is going to be executed after the current one. Exception is that there is some phenomena that has happened that brings me away, brings me into another piece of code that doesn't belong to me. Typically, I like to do this interactively. I start to ask you, what are exceptions that you know, right? What type of exceptions you know? One of the types I already mentioned are I/O, input-output exceptions. That is, I have a peripheral, and the peripheral asks for my attention, says, I have received a packet, I'm the network card, I received a packet, someone has to come and relatively quickly empty my buffer from the megabytes that just came in, because otherwise my buffer will be full. And the way we want to do it, we typically want to do it, is with one type of exception that, again, we call interrupt, that makes that I am doing my PowerPoint, I'm executing it, but well, at some point, if there is something more urgent, I will stop for a moment the execution of this. I will go to take care of the buffer, maybe copy what has come in the network card into a buffer of the operating system for this link, and then I will come back to my PowerPoint. And the idea is that, of course, if this is sufficiently fast, the user will not notice anything, and whatever needs to happen will happen exactly at the right moment. This is also what is called a non-terminating exception, right? There is not something happened, but this something doesn't terminate the program that I am executing, doesn't terminate my PowerPoint. On the contrary, it's the principle is that I want it to continue it as soon as possible, but I want to take some time to do something else. Now, I want you to go back maybe and revise a little bit, if you are not clear, all the exceptions that exist. You probably should know a number of them. Other types of exceptions that exist, for instance, some that are terminating, typically are arithmetic exceptions. You try to do the division by zero. This is a problem of my own program, right? I'm writing something and I make somehow a mistake and I divide something by zero. And since the operation is not defined, there is nothing that can be put in the target register. And what typically happens, it depends on the architectures and so on, but what typically happens is that there is an exception that is thrown to say something that should never happen has happened. And this is typically a terminating exception, right? You try to write this if you write some C, right? And you write a division by zero, the program will terminate by saying division by zero. It is the operating system that will get this exception. So what you go and execute at the moment of the exception, division by zero, is the operating system that will look at what is the cause of exception and will say, okay, this process is doing something stupid, kill the process and give a message on the screen or on the console that says this is the way the process has died. So this is a case of non-terminating exception. So it's a it's an exception, but non-terminating. Most of the exceptions today are non-terminating. I have a doubt that I may have said the wrong thing. This is an example. The last one, the divide by zero, is an example of terminating exception. So I'm sorry if I say the opposite. Most of the exceptions nowadays are non-terminating. There are a gazillion of mechanisms in our processors and in our systems in general, in our operating system, that demand the use of exceptions as a way to make the execution continue. So again, I want you to think and go and revise a bit what are exceptions that are important, and there are at least a couple of examples that come to mind that are absolutely essential to the functionality of, I don't know, this laptop. Can you think of them? Let's make it a little break so that you have a time to really think of all the exceptions that come to your mind. So I hope you took some moments to try to remember as many types of exceptions as possible. I'm sure you know many, or you can imagine many, but there are two types of exceptions that are so fundamental that we need to make sure that everybody remembers them, because we are going to sort of discuss them at multiple times during this course. So let's say this is a little parenthesis that is still a reminder of basic computer architecture. These two exceptions that I want to discuss are the virtual memory, the exceptions that support virtual memory, and will be more precise in a minute, and timer exceptions that a little later also I'll try to remind you of what they are. So let's think of virtual memory, which I hope it is very clear to you, but again, I want to be absolutely sure, so I will repeat in a few words what is virtual memory. The idea of virtual memory is that the addresses that you know of for the data in memory are not the real physical address in the system, but there is an indirection table that translates, oops, it's very difficult to draw, but I think you get it. There is a translation where when you say an address, so when the processor, the programmer issues an address, it gets translated into a corresponding physical address, which is the one that is used to access the cache and the memory. So it's just an indirection, right? It's just a translation between some virtual address that the programmer uses and the physical address that the memory uses, right? The physical address must be within the boundary of the memory that you have in your system. Why is this of any use? Why anybody would want to do that? There are essentially two reasons. The first one is to give the operating system, which manages this conversion table here that is called page table. The purpose is to give the operating system that manages this page table some freedom on how to handle, move around, do things with the physical memory. In other words, you have a virtual view of memory, an idealized view of memory, for instance, you think you have the complete addressing space or a very large addressing space, much larger than the physical addressing space, than the actual memory that you have, and you believe that this is all yours, as if you were the only user of the computer, which may be, and typically you are not, right? There are other processes, maybe even other users. But you have this impression of having everything for yourself because you have your own virtual address, your own, you say, address 0, and this address 0 may be a specific address, physical address for you, and someone else or some other process in the same operating system in the same machine thinks also to have the address 0, but is actually physically some other address distinct from yours, right? So there is this versatility that the operating system has in where to place things, and maybe to figure out that you want more memory than physically available, and then some parts of the data that you have in memory could be moved onto the disk because maybe they don't look very important or very frequently accessed, so that there is enough space for you. So you have this idea of a very, very large address space. You don't know how much physical memory there is, and the operating system takes care of this management. So this is one of the important reasons for having this virtual memory, this translation, this indirect access to memory. And the other advantage is also to screen, to separate the different users, right? I see only some physical addresses that are in the translation for my virtual pages, but some pages that have a physical address, if they don't appear in my table, there is no way I can access them. And this way, if it is done very well, we'll come back very much onto these kind of problems at the end of the course. But if I don't make mistake, if I don't have problems, I can use this mechanism to preserve the privacy of the different users, in the sense that I don't have any way to issue the address that goes and read the data of some other user, because it is behind this table, essentially, right? Okay, so this is the reason why we have, and is a little summary of what is virtual memory and why do we have it. Now, how does this usually get implemented? There is one indirection more. So every time that I want to access one element of memory, I actually have to do the translation, and I have to do a load before I do the real load, right? Whenever I want to load something here, or let's say something from the cache if I'm lucky, I need to translate. So I have to read this table, which is a big table also in memory. And so I have to do 2 loads for doing 1 load, which is a catastrophe, because already we know that the memory is low. So the actual implementation of this system is that I have my processor here, I have my cache and all the memory hierarchy that starts here, and in between, typically in between, it can be placed slightly different, but it doesn't matter to us now. There is what is called a TLB, a translation look-aside buffer, which is essentially a cache of the most frequent translation from this page table. This page table may be extremely big, depending on what has been allocated for you by the operating system, how much memory you consume, and so on and so forth. This is instead a hardware structure, is a bit like a cache of the most frequent translation that you request. And if you find a translation inside here, so you issue here an address, if it is found here, it is translated into a physical address, and then you start looking in the cache. And if you construct reasonably well this system, maybe you can do this. This can be even combinational, and so within the same cycle, you arrive to the cache, and the address arrives to the cache. The cache can respond, and so on and so forth, right? But the TLB is essentially a cache, as I said, is something that contains some of the frequent translation. So every now and then, it does, it does not find the translation that I want, because it has only maybe 64, maybe 100, maybe 1000, maybe at most different possible translations inside. And so what happens when there is a miss? So let's be clear. I hope for many of you is clear, but I'm pretty sure that there is someone that is maybe less clear about this. What is happening in my processor is that, for instance, I'm executing a load $R1 something something, right? I'm loading something from some address, okay, maybe $R2, from some address, and in the middle of it, my processor has started doing the load, is starting to go, it would like to go to the cache or to the memory to get the value that can be put into register R1. In the middle of this process, it turns out that, in a sense, I don't know where is the address pointed by R2. I don't know where it is physically in memory. And this is this miss. So what can I do? In a sense, it's too late to do anything in the execution of the load, right? I'm executing the load. I'm in the middle of maybe the pipeline. And so the mechanism that is used is that of exception. And here it is. The TLB miss. The TLB miss is one of the exceptions that maybe happen most frequently in our processor, or at least that are most important to the actual everyday functioning of our system. What happens, I hope you remember, and I'm going to repeat it extremely fast, but go and read somewhere if you are not clear, is that I need to understand why there is a miss. And there are many reasons for this miss. The simplest reason is that this TLB, as I said, is a cache with the most frequent. Well, maybe you access something that is not so frequent. So the operating system goes in the page table, says, oh, but there was this translation that was the right one. It was not in the TLB. Let me put it in the TLB. And what happens? The operating system must sort of say, execute this load again, because I fixed the problem. Now the translation will be possible. Go and execute this load again. And we'll come back to this example in a minute, because that's exactly the kind of mechanism that is problematic for us potentially now. But somehow I go and I re-execute the load word. Now this R2 address that I sent in here is translatable because I just put the translation. It will be no miss anymore, and I will be able to do the load. Okay, so this is the important mechanism of when things go bad, because I have a TLB miss, but not as bad as in other cases. Other things that may happen is that I find it in the page table, but is marked as on the disk. It's a page that is no longer anywhere in the physical memory, so there is no translation that I can put here because it's not there, but is a legitimate page or a legitimate location in memory that you may want to ask. And so what the operating system has to do is to put back from the disk this page into memory somewhere and update this translation that now doesn't say anymore it is on the disk, but it is at some specific address in memory where I just put my page. And now, again, exactly as before, I can load in the TLB this translation, and I can reissue the load, and I will find the translation, I will find my data, everybody's happy. And then maybe the most negative situation when I have a TLB miss is that I look in the page table and I just don't find the translation, because that page that address that you requested doesn't exist, right? You try to do on your GCC compiler, on your C compiler, you try to access one address at random. So you write a pointer at some address and you go and read from that pointer the value of the variable. You'll have an exception, and your operating system will decide that it is a terminating exception because there is no point. You asked something that you should not ask and that it doesn't mean anything, so you made a mistake. Okay, so this is one mechanism that is extremely important that you have clear. Again, go back to your notes of basic computer architecture if it is not clear, because you need to have a very clear idea of how the virtual memory system works and what a miss in a TLB becomes in terms of exception, and what are the things that happen in case of this exception. So this is one of the two exceptions that I wanted to mention. The second exception that I mentioned before that is important to bring up in this case, because it's one of the, again, most important exceptions in our system, in this laptop that I'm using now, it is the timer exception. We have all now operating systems that are multitasking, multi-program, in the sense that there is, in this moment, there is a Zoom that works, there is PowerPoint that runs, there is my mail tool perhaps running in the back, and a gazillion of different programs or jobs in the operating system terms and they are called jobs or tasks. All of them run at the same time, and I'm doing quote, you don't see me. What does it mean at the same time, quote? Well, forget multi-threading in my processor and multi-core processors. We'll come to that in a minute, but is not the reason. I have a single processor. I have a single PC normally in my processor. I can do only one thing at a time. So how do I give the illusion to the user that there is at this time both Zoom and PowerPoint running? Well, I give an illusion, exactly as I said, by stopping having one of them run for some time, 10 milliseconds, 100 milliseconds, and after that, going and executing a bit of the other program. And then after 100 milliseconds, another program, and so on and so forth. And if this time to change from one to the other is relatively fast, I will not notice that actually PowerPoint is not continuously working, but is working only every now and then. Now, how is that implemented? How do I stop a program from working? It's exactly the kind of things that I was saying before, right? It's a jump, is a change in program flow that is out of the control of the programmer. PowerPoint, who wrote PowerPoint, writes only the functionality of PowerPoint. You don't exit PowerPoint unless you do quit, okay? Otherwise, PowerPoint will run forever. And you want to interrupt it, you want to stop the execution of PowerPoint to go and do Zoom instead. How do you do it? Again, this is an exception, right? You have a timer that every 10 milliseconds, 100 milliseconds will go and stop the execution of the current program, will save all the state of that program somewhere, and will take out the state of another program and will launch the execution. So it's again a non-terminating exception in the sense that I take the state, I put it somewhere, I execute something else. At a later time, there will be another exception. I will put back the original state of the program and I'll continue the execution. And the assumption is that the program itself or the user of the program will have no clue on the fact that we didn't execute continuously this program. So again, is a non-terminating exception because I have an exception that stops the program, but then I continue the execution at a later time of the program. And so these two mechanisms are extremely important into our contemporary systems, and we have to do something for them. let me clear all this little mess and come back to the situation. So let's take this snippet of program here, right? I have a number of instructions. At some point, I arrive at the load, and then there are again more instructions. Now, let's come back a little bit to what we just said. This load may load something from the address T6 plus 8, addressing the value in T6 plus 8 from that address, and maybe this address is a TLB miss because it is a translation that doesn't exist. So it's totally legitimate to do this load word, but it will incur an exception. Now, I said before, what has the operating system to do, which was simply to read in the page table, figure out the correct translation, put it in the TLB, and I said before, restart the load word, reissue the load word. So how does that happen? So the exception is a jump or a call. Maybe it's better to call it a call. It's like a subroutine call, but it's a subroutine call that I didn't write in my program. I wrote load word, something bad happened. Somehow this special call has been done, and I executed that part of the operating system that took care of reading the page table and so on. And somehow what I want to do is a sort of return, right, at the end of this operating system function that comes back to the load. So how do I reissue the load? I do a jump, essentially, of the execution again on the load. Right? This is the only way, the only natural way, at least, that I have to handle exception and to make them non-terminating. Right? If I want to not terminate the exception, I come back with a jump at the end of the exception handler, and I continue the execution. Okay, this is great. And this is what is done in my original processor, the one at the beginning of last week. It was particularly trivial to do that, right? Because I am one instruction after the other. If in one instruction, that is the load, I get this problem of the exception, I finish doing these instructions by putting any rubbish in T3 in this case, because of course I could not do the load. I do the jump to the exception handler. The exception handler does what it does, and in the end, it will do a jump back to the load. I execute the load again, and everything works. But now let's look at what happens in this processor of ours of today, the one that we are trying to do. The actual situation in this processor that happens is what you see at the bottom of this, in the bottom example where it is written imprecise. The actual situation that we have, because we've done it on purpose, is that some instructions at some point in time, some instructions are executed, some instructions are not executed, but this is not in order. It's not if I now detect an exception on load word, if I now have the TLB that tells me, oh, there is a problem with this load that you are doing, it's not that every instruction that is before has already been executed and every instruction that follows has never been even considered for execution now. Now the situation is that I have maybe instructions that are before that have not been executed because maybe have dependencies that are not honored yet, and instructions that are after my load that have already been executed and because they were ready to be executed, and so there was no reason to hold them back. Again, this is exactly what we are trying to do, and we are happy that this is happening. But now we are not happy with the exceptions, because what do? How can we tolerate that the exceptions are imprecise, are not precise? I have no reasonable mean, at least, to come back and execute, because if I come back like before to re-execute the load, for the load all is good. In fact, again, whatever I said before is still true. The load will work because the TLB has been fixed and so on and so forth. But who will ever execute the AND and add E that I have here? Nobody, right? Because again, the mechanism is that of the program counter, right? I come back loading the program counter with this one. The two instructions that are before have never been executed. Maybe they are somewhere, you will say, in my reservation station, so eventually they'll get executed. Maybe, but then there is this one, right? This one I had already executed, but now I'll fetch it again because again I'm just jumping to this instruction and I'll fetch and decode all the instructions that follow if this one doesn't create again a problem. And then I'll come here and I'll execute again this instruction. And maybe not per chance, I wrote an instruction that I cannot execute twice, right? If I add 4 to T0, and if I do it twice instead of once, well, the value in T0 is clearly wrong, right? So I cannot simply execute again this instruction. So we do have a problem. We have a fundamental problem that we need to implement precise exceptions. The exceptions that will be natural to implement in our out-of-order machine are imprecise. I'll discuss this a little bit more at the end of today when we look at a little bit at the history of things, but there was a time where imprecise exceptions were okay. And I'll explain why. Now it's absolutely intolerable, right? Because we rely on exceptions for the normal operation of our processor, of our system, and we rely especially on non-terminating exceptions where we need to come back and continue the execution. So we need to find a solution for that. The way we go about this problem and the way people have managed to solve this problem is a fundamental observation that seems maybe a little trivial, but you need to sort of stop there for a second and understand how, in some senses, deep is a deep observation. The observation is that we can do whatever you want until the moment you observe what I'm doing. It's a bit what I was alluding to before, right? I mean, I said before at some point, oh, you have to, at this point of the program, you need to have in F0 a particular value. Well, it's not totally true, right? It has to be there only if you are allowed at that point to look into my machine. In other words, I can separate what I do from what you can see. The reality of my execution is a different thing from the illusion that I give you on what is the execution that is appearing. Again, another way of saying this is that if I lie sufficiently well, if I tell you lies with sufficient care, it will go well. I can do whatever I want, but I will learn to tell you that things are happening in a specific manner, like sequential execution, like if I were to do things in order, you cannot tell the difference because all that you can see is the state. So it is particularly important to separate then two things in this reasoning. There is the machine state, and state means, for instance, any register, the value of the register. Does it contain a 0 or a 1? Can be split in two parts. What traditionally we call architectural state, which is the state that is known by the programmer, is the state that is part of the architecture. The architectural manual says there are 32 registers. You know, as a programmer, that there are these registers. What is in there is visible to you, is architectural state. But then there are plenty of registers that you don't know necessarily that they exist. My pipeline registers, nobody tells you in the architectural manual, in the contract with the programmer, where I have internal registers, how many, what do I do with them, and so on. This is the microarchitectural state, and the microarchitectural state is exclusively my problem. So what I can do is to use my microarchitectural state to advance in execution however I want. The only condition that I have is that I need to update the architectural state as if I were doing sequential execution. So now I have this new state that is, when do I tell that I've done something? And this new phase typically is called commit, or others call it retire, or others say graduate. An instruction graduates the moment I tell the user, means I put in the machine state the value that that would have been there at this point of the sequential execution. And maybe this has nothing to do with what I'm actually doing and how I'm actually doing things. For doing this, the critical part is a reorder buffer. I need to have a unit, this commit unit, this lying unit, that has no other function than to look at things in the original order and update the state of the machine in the original order. Let me do a little pause here. What is the state? I already said the architectural state. I already said the registers, right? And my manual, my architectural manual tells me about all the registers, maybe the flags in processors that have flags, and so on and so forth, special registers. This is architectural state. This is what has to be updated in order. What are other things that are architectural state? The program counter is, right? At some point, if I do an exception and I want to know what was the program counter at the time of exception, so maybe you will call it the exception PC, this is architectural state. So if I have to give you the exception PC, I need to give you sort of the right value, the actual value that will be known in an in-order machine. What else is architectural state? Of course, memory, right? Memory is, I know that I have 1 billion location of memories in my PC, and this location of memory, again, should be updated in order as if you were doing a sequential job. Again, maybe you don't, but you have to give me this illusion. And so how does this commit unit that gives this illusion? Well, it's another buffer. And if you remember, the picture before is this unit that is at the towards the end of the machine between the functional units and the write back, the register file. So here it is. The commit unit is between here our units, as I just said, and the register file. What is the sense of this machine? Is the same machine that I had at the beginning of today. Towards the beginning is just I turned it 90 degrees. You still see the fetch and decode unit, the reservation station in front of all the functional units, this reorder buffer or commit unit that writes back in the register file. And what is important to look at, to understand out of this picture, is that there are two paths that our results go through. One path is when I have a result, I put it in the commit unit, and in a sense, at the right time, I put it in the register file and the load store unit. Basically, I put it in memory. But in fact, I use this result immediately to advance as fast as I can in the execution, completely disregarding, in some sense, the register file. So the register file, in some sense, became a peripheral thing, a decorative object that I update when I can, when I should, so that people will find the appropriate state in there. But my machine is actually advancing without looking really at the register file, is getting all the information directly as fast as possible. Right. So I hope you see these two completely different paths, right? There is the path of execution that is use whatever you can as fast as you can and ignore the order of the instructions and all these little details. And on the other side, there is this I need to lie so that if someone comes here and looks at my registers, finds them in good state, this unit here is going to put in order the information into the register file to help in that situation. So let's go back for a second to this reorder buffer. How does it work? It does work in the following way. The first thing is that it is a ordered structure. So contrary to the reservation station where I was saying they are completely in disorder, is a parking lot. They are all the parking spaces are equivalent. You just pick one which is free and that's it. Here you have typically it could be a circular buffer, right? I have some memory for this, some buffer of some size, but I have a pointer to the head and a pointer to the tail. Okay, so I know what is the oldest instruction in here and the newest instruction in here. And what do? Every time that I get something from the fetch and decode unit, every time that I decode a new instruction, I go at the end of the list and I add my instruction here. I add my program counter. Where did I get this instruction? I put here the tag that I assign to this instruction. That is, at the same time that I'm putting the instruction here, I'm going to look for a position inside the appropriate reservation station. I'll find a position, I find a name for the reservation station that I used. This is the tag of this instruction, right? There is the same tag that I will use for every dependencies. So I'll put it here. I'll put here the destination register of this instruction, so where this instruction will have to write the value, and what is the value that it will have to write. And of course, the value that it will have to write in the register, I don't know because I just fetched and decode, right? So when I introduce a new instruction, it's going to be something like this third instruction here, right? I know the tag, I don't know the value. And as the execution progresses, I will inform from the execution unit exactly in the same way that I inform all the reservation station. I inform the reorder buffer of all the new results. And I look into here if there is the tag that has been of the instruction that has been just executed, and I replace the tag with the value. So I obtain something like in this first instruction, there is no tag anymore because it has been executed and the value is now in the reorder buffer. So now this instruction, whichever it is, whichever it was, and whenever it was executed, but the result in F3, this instruction resulted in a new value for F3, and this result is this value here. Okay, so I hope this is clear. No, I start with instructions where I have a tag, but I don't have a value, of course, because I don't know what is the result of the instruction. And eventually I will know that the tag disappears because I don't care anymore, but the value that has to go into this register is a specific one. I want to be a little bit more precise on something I said because I said it maybe purposely wrong or ambiguously. when I search for a result, when I announce from an execution unit a specific tag and a specific value from the execution unit, I said, if I find it here, I replace the tag with the value. Now, this is a little bit incorrect, right? This is a correct sentence when I go in the reservation station. I don't know if the reservation station needs or doesn't need this value from the execution unit, but I look, and if I find it, great, I replace the tag with the value. Maybe I don't find because there is no instruction that really depend on this value at this point in time. Here things are a little bit different, and I just want you to notice it because it's part of understanding this mechanism, right? Here, all instructions are here. So all tags that are currently employed are here. So I will always find once and only once every tag, right? Because this is the original instruction that was given that tag. So if I'm executing something, the instruction exists, and it's only that instruction that can carry that tag. So there is only and always one and only one occurrence of any tag that comes from the execution unit. Okay, just to be a little bit more precise. Now, I said how things enter in this reorder buffer by going to the end of the reorder buffer and placing any instruction that I decode prepared with the tag and, of course, no value. I said I wait from the execution unit all the tags and value couplets, pairs, and replace the one instance in this table where this tag was occurring with the value. And the third mechanism that is important here is how do things get out? And they get out by looking at the head, and I look at the head and I look at the first instruction, and if the first instruction has a value and doesn't have a tag, it means that this instruction, which is the oldest one in the machine, has been executed, and it's time to announce to the user, to the world, that we have executed this instruction. So I take this value and I put it in register F3. Now, if it turns out that this first instruction has not yet been executed, but for instance, the second one has been executed, I do absolutely nothing, right? Because what this reorder buffer is doing is to put the results of the instructions in the register file at any time, but in the correct order. So I will never take the next instruction and put it in the register file, because this is exactly what I'm trying to avoid through this reorder buffer. I'll always consider only the top one. If the top one is fine, I commit. I lie. I say, oh, I just did it. Maybe I did it long ago, but I'll tell, oh, I just did it. And if it is another instruction that is done, if this one is not done, I will do absolutely nothing. I will keep waiting until the oldest instruction is executed, and then I will announce. And this corresponds exactly to what was said a minute ago, of sort of updating the state in order of instructions coming from the program, so as if I were in a machine that is sequential, but doing whatever I want independently from this commit unit in reality. So I hope the mechanism is relatively clear. In a minute, I will do a few examples in detail that hopefully will clarify some details if you have. But I want to point you out to a couple of things that are maybe strange at this point. We have spoken of these fields, the tag, the register, the value. There are a few other things that I drawn on this reorder buffer, and maybe it's not completely, absolutely complete as a reorder buffer, but is a reorder buffer that will do all the things that we need to do in our examples, in our, let's say, elementary processor. There is a column, or there is a field that says, did this instruction have an exception? I will go back there in a minute. There is a column that I mentioned, but I never said what for, where I put the PC of the instruction that I just fetched and decoded, right? When I insert this program counter. Why do I put the program counter here? I will invite you to stop for a second if you want the video and try to think, how am I going to use these two fields, and in particular maybe why there is the program counter of the instruction here. And the last one that I didn't mention, but I hope is the simplest one to imagine, is the address. Why do I have an address? Is because I'm updating here the architectural state, and the architectural state is equally a register and, as I said before, the memory. So even if I have an instruction that is a memory instruction, a store, I have to write at a given address a specific value, the value I'm waiting to compute, and I'm waiting for the load, some other operation to complete and give me the value that I need. Once I'll have it, and once this instruction will be at the head of the reorder buffer, that is the oldest instruction, I will be able to write to this address the value. So it's exactly the same thing. As I modify the state through writing in a register, I modify the state through writing by writing into the memory. Both things are part of my lying to the world about when I really did something, right? So I need to use the reorder buffer both for register destination and for address or memory destinations. Okay, so as I said, I will now show you a few examples. Maybe we just need to go for a little observation that basically structural hazards have disappeared already. At least the kind of structural hazard that I pointed out earlier on have now disappeared. We had this problem of having only one write back, one port to the register file, for instance, or in any case, a limited number of ports to the register file. And maybe multiple instruction terminating. Well, now that different instructions that terminate write into the reorder buffer, and the reorder buffer will send only one, the oldest, to the register file. So there will be no structural hazard. There will be no competition for this port to the register file. We know there will be one, and it will be the oldest at most, or none if the oldest is not solved yet. This is a simple example of functioning of the reorder buffer in normal situations, maybe similar to what I was mentioning before, but in more precise way. I will do this on the board normally, but since we don't have a board and we are not in presence, I added 2 or 3 slides that hopefully help seeing the different situation. So the situation here, if we were in this situation on a specific cycle, I will look into the head and I will see that I can write F3, the register F3 with this new value. So I will simply commit and advance my head to the next instruction. Now, if the next cycle I find myself in this situation, I will just do nothing, because I would have to clearly this instruction, I think we already looked at the same instruction a few minutes ago, is clearly a mem instruction, but I see it from here because there is the destination that is an address, so it's certainly a store, but I need to store something that has not been calculated yet. So I'm waiting for this value to arrive, and therefore I do simply nothing because I have to write the state in order. So even if there is here later an instruction that has already been executed, I know that eventually F3 will contain this value. I am not putting this value now because, again, I want to lie and give the impression that I'm doing things in order. So I'll keep waiting, and at some point I will get the value for a number of different tags that were there. In this specific case, the first one now in this cycle is known, the address and the value, so I can write at this address that value, so I can do the store in the cache. And for instance, the cycle later, because again, I have the information, I can write the F5, right? So I hope the mechanism is clear, right? I just write things in the original order that I had. Now, how this exactly connects with the precise exception, and I hope it is clear to you already, but or you can imagine easily, but let's say it explicitly. The idea is that when I have an exception, when I realize that maybe a store or a load would like to access an address that I cannot translate, my normal reaction will be to immediately raise an exception and say, oh, we can't, let's go and call the handler to do something. But here you don't do. We are going to simply mark the entry, and this is why we have this first column here for the exceptions. We will simply mark there and say, oh, look, these instructions had an exception. And we will not do anything until this instruction that had an exception is ready to commit. And of course, we cannot commit it because something went wrong. So there is no point in writing something in the register file because this instruction cannot take place. Maybe it was even a divide by zero. Whatever it is something that could not complete. But it is at that point that we'll raise the exception, because every instruction that was before it has been not only executed, but also announced to the register file and to memory, that is to the programmer through the state that is visible to them. Whatever follows, I'll throw away. Are instructions that I have maybe executed, maybe I'm executing, maybe I have not executed yet and they are just waiting. All these instructions should not have ever been brought in by my out-of-order machine. It's my abuse to have done something about those. And since I want to give the impression the correct impression, all these have to just disappear. And here is the example that, again, I hope it is sort of clear also from what I just said, but maybe is more visible in this. I think it is the same situation as before, but I have here this store. Again, we say it has an address and a value, and it turns out that this address is not in the TLB, so it's a TLB miss. I do nothing, and I record that this is an exception. Now, I ignore it. I ignore the problem, and I continue committing. So I see also here that F3 has to be given this new value, and I commit that. So I go ahead as if nothing happened until this instruction become the next one to potentially commit. And I repeat again, I cannot commit it because clearly something went wrong. I see it from the exception, but this is the time to mention, to report the exception, basically to load the program counter with the program counter of the exception handler. Before doing that, though, I do one more thing, which is to move the tail on the next entry in the reorder buffer, which essentially means trash everything that was later in the reorder buffer. This clears the word from the instructions that I maybe was executing but should have not done. And now you understand that it is exactly the image that we had a few slides back of the program in green, red, and blue, I think it was, of the precise exception. Anything that is before, in that case, it was a load, the memory access that had an exception, has been executed and the result is in the register files. The load or the store in this case is having a problem, and before we can execute, we will put in the program counter the value, the address of the handler, and everything that is later apparently has never been taken into account. It's not true, I'm lying, right? But there is no trace of anything that has been done past this instruction. And so we have managed to implement precise exceptions on this out of order machine. So we have managed to reconcile to fundamentally different or potentially incompatible problems. On one side, to go as fast as I can, irrespective of the original order of the program, and give the impression that we are going in order, because if someone stops us through an exception, they can come in and they will see what we have done, and they will need to have a consistent state and not the messy state that intrinsically our out of order execution generates. Before we move on to something else, or to some other aspects of all this, I want to go back to one question that I asked before, because it's still unsolved, is why did I put the program counter here at the moment I fetched and decode the instruction? And I invite you to maybe stop a bit the video to think about it if you want, because you should find a solution, but I'm helping you also by noticing it here, right? It's clearly connected to the exception. The reason I am putting here the PC is that now I have to, in a sequential processor, what I will take is I will take the program counter of where I am. I just fetch the instruction, I decode the instruction, and I would have looked at it and tried to and figured out that maybe I cannot do the access because there is a TLB miss. And I will take the PC and I will put it into whatever is the name that you give to this register, but there is always in a processor something that is the exception PC, the PC, the program counter at the time of exception, right? It's called $EA in MIPS, in NIOS. If you are familiar with MIPS, it's somewhere in the coprocessor 0. There is one register for the exception PC. It doesn't matter what it is, but it's fundamental for my functioning of non-terminating exception that I tell which instruction had the exception, right? So that this is what is used by my exception handler to come back here and execute again the same instruction or execute the next instruction, depending on the type of exception, on the mechanism, and so on. Now, here my PC, my actual PC where I'm fetching and decoding, has nothing to do with this instruction, right? This instruction has been fetched and decoded long ago, and my if I go back one slide, my fetch and decode unit is probably fetching something at address 10 million, whatever, 18, right? Is fetching the next instruction. So the program counter, the real program counter that I'm using to go and fetch stuff is running ahead in a uncontrollable way. What I need to put in the exception PC is where was the instruction that created the problem. And this is exactly why I put this value here, because this is the value of the PC, that is the address of this instruction in memory. And so I need to have this because the moment this exception arrives to the head, what I need to do, I don't need to do anything about this address and anything else because there is nothing to be done about this. There has been an exception, but what I need to do is to take the program counter, the original program counter of this instruction, and put it into the exception PC before jumping to the exception handler. We are finally getting towards the end of our trip. I think that most of the mechanics of our out-of-order execution should be clear by now, but there are a few things that we want to a couple of things that we want to look at. And one in particular is something that I hope has bugged you somehow. And if it hasn't, I hope that as soon as I tell you, you'll say, yeah, there is a problem there, right? At some point, I was saying, right, when we were looking at our reservation station, I was saying, okay, so we fetch and decode an instruction, and if there is a dependency, or if there is no dependency, we take the value from the register file, which is easy. If it is not, if there is a dependency, we put the tag of the instruction on which we have a dependency on in the corresponding tag here in the reservation station. But the question is, it's easy for us to understand this because we understand dependency by looking at the code. But if I have the view from the fetch and decode unit and I'm just decoding an instruction, how do I know on which past instruction there was a dependency and if at all there was a dependency? In fact, I want to make a pause. Again, I don't know if you were bugged by this problem, but you should, I hope. You agree, be disturbed by the fact that we sort of gloss over the problem, but is actually a fundamental problem if we have to implement this architecture. So I'll make a pause and I'll let you think, do I have somewhere in the machine the information that I need to know if an instruction has a dependency on another instruction? A new instruction that I just fetched has a dependency on any of the instructions that are still inside the machine, or if I can simply go and read my register file. Once more, I hope you really take the time to think, because I believe that you should be able to find the solution to this question. And the solution is very simple. This information is essentially in the reorder buffer. The reorder buffer has the history of all the instructions that are not yet committed, and it knows about their destination registers. So I'll illustrate this with a few examples. You can read maybe the slide for a more precise text. But the point is, I can go into that. And if I have a new instruction now that says, I need F1 as one of the values, I can go and look if any of the instructions that still have not committed their value in the register file and see if any of them writes in F1. And if I see that nobody is writing in F1, it means that I have no dependency from any of the instructions that are still in my processor. So I can go and it's safe to read the register file. If my new instruction that I am inserting now in the tail, or I'm going to inserting in the tail, for instance, asks for a register that is somewhere in the reorder buffer, what I can do, first of all, I understand that I do have a dependency, and so I have to honor that dependency. But what I can do is that I can go and see if there is a value already for that instruction inside the reorder buffer. And if there is a value, this is the value that eventually later on will go into the register file, but I can bypass the register file in the spirit of I don't care of the register file, I want to go as fast as possible, and I can take this value, bypass the register file, and use it as an operand. So when I said before we read either the register file or we put the tag, actually is not necessarily completely true. Maybe we go and we find in the reorder buffer the value ready for us. Another case is if I'm looking for a specific register, for instance F5, and I yet don't have the value. And this is exactly the case where I cannot read the register file, not even bypass the register file. I simply have a dependence on a value that is not yet computed. So since I see here that I don't have the value, what I do is that I take the tag, and this is the tag that I have to use in my reservation station to say where my value will come from. So how do I find the tag of the corresponding instruction in case of dependency? This is the answer. I see here my register. I don't have the value ready. I have the tag. I use the tag. And last but not least, what might happen perfectly well is that there are multiple copies, multiple occurrences of the register that I'm looking for. If my new instruction depends on F3, I have maybe multiple F3 here. Is this surprising? Absolutely not. What does it mean? It means that there was an instruction a bit older that was writing in F3, and there is a newer instruction that will also be writing in F3. Remember my example of program at some point about this write after write dependency? There was a write after write dependency in the code, which is totally possible, right? So what do I do in this case? Well, I guess it is clear, right? That this is an older instruction that writes in F3. This is a more recent instruction that writes in F3. If my now latest instruction is the one that I care for, clearly the value that matters is the one closest to me, so the most recent one, so the one in this instruction. And it turns out to be the same case as the last one that we have seen. I go and I look at the value is not here. It is a dependency on the instruction tagged as ALU3. So the only thing that I have to take care, and this is the reason for this arrow towards the top, is that I have to go and look at all the elements in the reorder buffer, but I also have to look at it from the end to the beginning. And things that are more close to me, more close to the end, are the ones that I care. If there are multiple, the others should be ignored. Now, whatever I said for register essentially applies also to memory, right? If I'm doing a load to memory, I also need to worry about the fact that there may be a dependence through memory that has not been yet written in memory, because I'm holding in my reorder buffer also all the stores. This is again clearly a store because it is going to write some value that is unknown into an address that is known. So this is a store that is pending to be done. Now, if I get a load to an address, I need to check if there is a pending store to the same address, and in that case, take the value that is here instead of the value that is in memory. So it's exactly the same reasoning as for the register. Is a question of whether there is a dependency through memory, with one additional maybe difficulty that doesn't exist for the registers. I always know which register I'm going to access, at least in all the architectures that I know of. So I know that one instruction is writing F5 and this instruction is reading F2, and this is known from the code time. Memory is more complicated, right? Because I may not know yet where a store is going to write, or I don't know yet which address I want to read. But the first case, I don't know where the store is going to write, is a little bit more complicated because I need to check if the value is here. But if there is a store here that doesn't have a target address, I simply don't know whether I have a dependency or not. And I will have conservatively to assume that I have one. So let's look a little bit more into the detail of the dependency through memory. What happens is that I have a link that is actually relatively complex, maybe not conceptually super complex, but complex in all the mechanics between the reservation station for memory, where I put the loads and stores that need their operands, right? A load need an operand, a single operand. What is the address that I need to load from? The store needs two operands. So what is the address I need to store to? And what is the value that I want to store? So there is a memory reservation station also for the memory, for obtaining the values. But this reservation station has one problem more. If I am a load, I cannot start unless I am sure that at the address that I want to start, I have no dependence on any of the stores that were before this load. Right? Because if I have a dependency, the value that I want is not the one that is in memory, but is the one that this store wants to write. And this is a problem that I don't have for other instructions. And so the fact is that people tend to sort of implement this in a slightly different way, where there are two queues. One doesn't have to be a queue. In fact, the load queue is not necessarily a queue, but the store queue is almost certainly a queue, that have that sort of take up a bit of a function of the reservation stations, or a reservation station with additional complexity, and partly the function of the reorder buffer. So here is an example of how one could implement this. Again, I'll comment on this in a few minutes, that actually this is not necessarily the way it is implemented, but is the logic way I need to implement all the things that I need to take into account to do a correct job. So here is an example of the load queue, which again is not a queue, but is the reservation station for the loads, and the other that is a bit of the reservation station of the stores, plus a queue that in some sense mimics the reorder buffer. And the load queue has one element more. So the load queue, again, consider it as the reservation station of the loads, which is very clear, right? There is here only the single operand that I need for a load, which is the address where I have to do the load, and either I have the address or I have the tag, right? So it's a normal reservation station, but with something more, which is to say what are in the order, because the store queue is in order, what are all the stores that were before me? What are all the stores that preceded in program order, in the original order in the program, this load? And why is that? remember what we were doing and we just described a few minutes ago for the registers, right? Whenever I fetch a new instruction and I have a potential dependency and I wonder whether there is a dependency on one specific register, I have to read all the instructions before me, which are all those that are in the reorder buffer, because I'm new, right? I'm just been fetched and decoded. So everyone that is in the reorder buffer is before me, and search for a potential conflict. Now, the load queue is different, is more complicated for whatever the phenomena that I just mentioned, is that sometimes I cannot determine if there is a dependency, because if I don't know the address of a store or I don't know the address of me load, I simply cannot tell if there is a dependency. I need to wait until I know the addresses so that I will be able to deliberate and figure out whether there is or not a dependency. But so I have to keep going and doing this check with all the stores that were before me. And now it is not the complete store queue that is there, because later on I've been parked here for some time as a load. The store queue will contain many stores that are after me, and I cannot care less of stores that are after me. They can write in the same address where I load, but they write after, so I don't care. So I need to have this pointer that shows me everyone that was before me, in the same spirit of the new instruction looks in the reorder buffer everyone before me, but it was trivial in this case. Here I need to have an explicit pointer to see among the pending stores which one were in front of me. I hope it is sort of clear, but it will probably become more clear through some examples. So take this situation, wherever it comes from and however we got here. This is, as I said before many times, is essentially the reservation station. So the first thing that we ask is, can I start any of these loads, right? And let's start from load 3. Again, there is no notion of order. They are certainly not arrived in this order. There are 2 parking lots that are unused, load 2 and load 5, and the others are used. And again, there is absolutely no sense that load 1 will be before load 3 in program order. In fact, if you think about it, is exactly the opposite in this case. So can I start load 3? Is it time to go and do the load? And of course, is the classic behavior of the reservation station. It's clear not, right? Because I don't have the address that I need to load, and I'm waiting for some calculation of this address. So this is a first trivial case. The second case that I may encounter is the fact that now my reservation station, my classic behavior of reservation station is honored. I have the value, so I have the operand, but I have this additional problem in the reservation station of checking in the load queue to figure out if one of the stores before me had a conflict. And so I have to go in the queue, look everybody before me, so these 3 stores, and again, I don't care of stores that came after me, but only before me, and see if I know the address of all of them. As soon as there is one that is unknown, I have a problem, or I have a potential problem, in the sense that maybe it will later turn out that one of these 2 addresses are in conflict with me, and then maybe this one will be this 0x10EF and so on, which means that this value and not the value in memory is what this load should report. So since I don't know if this concerns me or not, I have just to wait. So the reservation station is, as you see, a little bit different because it checks for readiness of the operands, but also has this additional dependency check to repeat every time until it will pass. Another example from this situation is whether I can start the LD4. And in the case of LD4 is again, it's in this case there is just one store before me, and it turns out that I can figure out that there is a conflict because it loads exactly from the same address where the store will save a value, but unfortunately we don't have the value yet. We are waiting for some calculation that will produce this value. So I have to wait, and the value that I will want when it will arrive, it will be this mul1. And the last case for the load queue that we are interested in is this one, where I go and check if I know of any dependency, and I find that there is a dependency before any of the addresses that are unknown. So again, it's the same situation as, and the same discussion that we had a few minutes ago when I was going into the reorder buffer looking for a register. I search from the bottom, I search from the latest, in this case, store that may have a conflict with me. If I do find a conflict, 87F, 87F, this is the conflict. If I find a conflict here, I don't care if there were older conflict maybe, and I cannot determine because they are not known. Certainly this is the conflict that interests me, and certainly this is the value that I want. And in this case, I do know the value, so I can avoid sending the load to the cache, so I will not even perform the load. I will bypass memory, exactly like in some other case before I was bypassing the register file, and I bring this value directly as a result of the load. So the load doesn't even issue as a load per se, has already the result. The result of LD1 for every other reservation station will be 6666 and so on and so forth. Finally, how does the store queue works in this situation? Well, it's actually a bit of a mini reorder buffer that takes only the oldest store and tries to do only the reorder store, but has to wait for a wink, an approval from the reorder buffer, because it should not only be the oldest store to be able to commit and to perform the operation of store, but it needs also to be the oldest operation at all, right? Every operation that was not a store but was before this store must have already committed. So the reorder buffer has to tell me that I'm the oldest instruction in the machine, and now it is time for me to commit. If I don't have something, I will not commit. If I don't get the confirmation from the reorder buffer, I will not commit. Great. We are at the end. I just want to mention a couple of things. One thing, so starting from the bottom of this slide, is that on the web, I mentioned in the introduction, there are a number of papers, sometimes some of the classics. This is one of the cases here. There is a paper by Smith and Pleskun on precise interrupt, and this is the paper that introduced the reorder buffer, actually explored several solutions to achieve precise interrupts in the context of an out-of-order machine, and they explore different possible solutions. Maybe it's interesting for you to go and see what are these different solutions. One of them is the reorder buffer, so it's exactly what people started doing from that moment on. But funnily enough, they explore other solutions that at that time, in that context, seemed possible, but not efficient, not particularly good ways of doing things. And I will remind you this paper in a few weeks, because we will be doing something in a sense totally else, but we'll have again this problem of interrupts in a completely different context. And surprise, surprise, what in that context makes sense to do is exactly the other idea that Smith and Pletskun did not prefer in this context. So it's interesting to see that something that is a workable idea, but not a practical one in a given context, something like 20 years later becomes useful in a completely different context. The other remark that I wanted to do about this slide, and is the first point that is done, the first bullet in the slide, is that everything that we have seen is usually described as Tomasulo algorithm in textbook, because without the reorder buffer to implement precise interrupt, something similar was implemented in a very old machine, as you can see, right? We're talking of 1967, so we are before pipelines, and we are therefore before any other form of instruction level parallelism. So there were already at that time machines that were going out of order, but life, not to diminish actually at all from Tomasulo for implementing it, but at that time things were easier because nobody would care for precise interrupts. And why that? Why would nobody care for precise interrupts? Because there was nothing like multiple users of the machine at the same time. You would have the machine for some time and do your job, and then go away. Someone else will come and will run their job on this machine. There were no things like interrupt I/O. Simply there will be polling to read the cards to input the program or the data. They will be read, and then the processing will start. And especially there will be no virtual memory. So there will be no need to have this complex translation that may result in a load to fail. A load never fail. A load, I go and I read physical memory, and I give a physical address when I read the memory. So the only interrupts is not that they were machine without interrupts, but the only interrupts that existed, the only exceptions that existed were terminating exceptions. There will be a division by zero. But then nobody cares if we left things in a strange situation. We just figure out that our algorithm doesn't converge, or we had a bad starting point and we make a division by zero at some point. We'll try to restart from a different standpoint, or we go and talk to our mathematician to try to fix the program, the math and the convergence of the program, and we run again. So no problem at the time of precise interrupts. And so precise interrupts delayed, usually, you see, practically 20 years to adopt something that was already okay and in commercial processors, to adopt it again for microprocessors took 20 years, took many years, because there was this problem of precise interrupts. So we are essentially at the end. I will spend only another 5 minutes and then we are done for something that at this point appears as cosmetic. So finally, now we have a good parallelism that we really extract actively from the program. What is the next part? The next part is almost trivial in this sense. I had only one ALU in my drawing. I had only one floating point unit. I have one unit per type. In reality, there is no reason for me not to put more units and essentially put them sort of proportional to the use of the corresponding parts of the instruction set. That is, if I have 3/4 of my instructions that are floating point, maybe I want to have 3/4 of my functional units that are floating point units, right? Maybe things are a little bit more complex in reality, but you understand the spirit, right? What do I need to change to my machine to do this increase in number of functional units. From the state we were, not so much, right? I can add them. The reservation station will look not only to the next instruction, to one, instruction that can be executed, but if it finds two, will start to will launch, will issue two operations on the same cycle. And it seems a relatively easy things to do from the point we were. The other thing that we need necessarily to do, because otherwise it's sort of silly to put many functional units, is to bring in multiple instructions per cycle. But in some sense, at least, and in some instruction sets, fetching and decoding several instructions is not really difficult. In some sense, is the multiple copies of the same decode unit that are in parallel, right? And think of the encoding of MIPS. I have 32 bits for any instruction, so I take 32 bits, the first word, and this is one instruction. In parallel, the second instruction, the next word is the second instruction, and I can decode it, and again the third and the fourth. I have to be just a little bit careful with the dependencies, because now dependencies can be between the things that are in the reorder buffer or one of the instructions that I'm decoding at the same time but was before me. But you can imagine that is almost a cosmetic difference, at least in a conceptual terms. And the same thing for the commit unit. I will want to commit not only one instruction at a time, otherwise my reorder buffer will be soon full. I need to support essentially the same throughput, so I will need to commit 2 or 4 instructions at the same time. Be very clear in your mind about the rules for committing multiple instructions. I look not anymore at the top instruction of the reorder buffer, but say at the top 4, but I will never commit the second if I cannot commit the first. So I look at the top 4, but I'll commit either the top 1 or the top 2 or the top 3 or the top 4, or actually none at all, but never anything in disorder, because again, otherwise I violate the whole semantic and purpose of the reorder buffer. And this brings us to essentially the architecture that, minus maybe one more detail that we will see in, I don't remember, 2-3 weeks, I think, minus one additional element brings us essentially to the architecture that you have into, for instance, your laptop, and most likely, I'm not sure exactly what you have in your smartphone, but probably some smartphones have something of already this sort. This is the path that we have done. Last thing that I want to remark, and then I'm really done, is the fact that I am a bit lying on the historical progression. The reality is that people did first superscalar processor, that is processor with multiple units, by not reordering instructions, but trying to see if perchance the order of the instruction fitted the availability of pipelines. One of the simplest example, and maybe even the first example of a superscalar processor, I think it was a MIPS or an alpha, but the idea was, in any case, to have 2 pipelines in parallel, one for integers and one for floating point, and the compiler will try to always put instructions in the order integer, floating point, and so on. And so if I fetch 2 and one is an integer, one is a floating point, I just insert them in order inside the pipelines, inside the 2 pipelines. If I don't fetch the right couplet, I insert only the first one in the appropriate pipeline. So people try to do this not to go out of order because of exactly all these problems in the exceptions, and only in a sense much later they accepted to try to go for these precise exceptions with the complexity, and of course naturally you will do a superscalar processor. Okay, we are done for today. We have done a long trip. It's a lot of the material of the dynamic scheduling is essentially here. What we will do in the next few courses is to try to do these things a little bit more realistically, in the sense that today we have cared for having data structures that contain the right data, but not necessarily to try to do things in a way that we can implement actually really in hardware. And we'll discuss why also maybe it's difficult to implement some of these things. Thank you very much and have a great week.